Let's discuss C++ for embedded. Are you still writing, using C for embedded? You know that you may be leaving performance, safety, and reliability on the table because C++ it provides huge number of opportunities and wonderfulnesses. Is that even a word? For embedded developers. Let's get through the list which I made into a slideshow. Let me close these windows because we're not going to be using that today. Let's dig into that. Ctrl-Shift F5, no? Did it not work? It did work. First of all, this will be my personal experience. It is not some theoretical what ifs and that maybe this feature is useful or not. No, this is explicitly what I have personally experienced when I switched from C to C++ for the embedded. This was an interesting graph that I accidentally stumbled upon at some random Google search which says that C++ has surpassed C. I don't know, take it with a grain of salt because there was a single source and I could not really readily see it in the source where this graph is coming from, but take it for what it is. It may not be far from true. Developers generally avoid going low level for the fear of shooting themselves in the foot. Right, all those raw pointers, losing resources left and right, no automatic garbage collection, that sort of things. It is a big deterrent for most of the people. However, in modern C++, it provides, first of all, it's a more strictly typed language as such, which allows compilers to have more information as to what is the code supposed to do, and they have better freedom of choosing what is the best way to implement what you are asking for in the target platform. One of the first things people do when moving from C into C++ is start using constexpr instead of #defines. And here is a, again, albeit somewhat contrived, but it does happen in real code example. So this is an example of where it's clearly a bug, but it won't be as easy to find once it is introduced. In C++, constexpr solves this completely. You just have the constant in calculated at compile time, and there is no double call to the get value because it's just there. Another place where constexpr and especially with the auto type deduction would be a differentiator between the use of C and C++. Another thing people generally tend to start using more or less immediately when switching from C to C++ for great benefit is enums instead of #defines. This is again a contrived example which shows a real life problem. So here what we have is an open file function that gets a mode, which in true C paradigm is always an int, right? And it can be either read, truncate, or write. But however, at usage, someone just misspelled read instead of read. A simple mistake could happen to anyone, not easy to catch visually, and the compiler would not complain about it at all. However, the read as a macro is defined as 1, which basically makes it truncate. So what you do here in open file, you accidentally truncate instead of opening it for read. And this sort of bug will not be caught at compile time ever, no matter how you play with it. C++, in contrast, using enums, not even plus enum, the new shiny enums, just a simple unscoped enum will still produce the desired effect, because when we say that open file only accepts the file mode, we cannot accidentally put a color enum into that, because the compiler will promptly yell at us, and that bug will be caught way earlier. And this is a real life example. So when we started working on our camera code, to the left is the C code that we inherited, which was like ripe with all those #defines left and right. And to the right is what the code looks like in the modern version of the code in C++, where we use constexpr, auto type deductions, and the enums. Another thing that is like low-hanging fruit when using C++ compared to C is the constinit functionality, which is introduced, I believe, in C++ 20. So to the left, you have a message buffer, which has been initialized in the main with a init message. So there is a runtime overhead because you need to store hello C world somewhere in your text of the program, and then you copy it over here. And you need to remember to do it, because if you forget, then you'll just print garbage. And depending on complexity of your program, obviously this is a simple example, but depending on complexity, it's not always easy to trace where the initialization happens, especially in a multi-threaded environment. In contrast, over here in a C++ world, this message buffer is const initialized. It doesn't have to be const, by the way. Const init just means it is initialized at compile time, but the value of the message buffer is not const. You can still modify it later on. And here is a real-life production code example of using constinit. So here I have a struct LED that does LED functionality, blinks LED pixels. There are 8 of them. And it's const initialized, which means the compiler reallocates and pre-initializes the object in the body of the text itself. So there is no runtime overhead. One of the big issues of C is inability to overload functions, which leads to proliferation, basically, of function suffixes and prefixes. Again, I'll have an example later on, but in here it makes the code much simpler when we define a single read function with a clear interface, which is then templatized based on the address width of the I2C bus, whether it's 8, 16, or 32 bits. But in your code, when you use it, you just say read, and depending on the type of the address provided, it will call the appropriate function. And here is an example of my code, which just does a whole bunch of static asserts at compile time for validation, which allows me to make sure that the API, in this case for the camera, that the data structures that are being passed over the wire are of an exact size. And if somebody changes one of those and one of the static asserts fails, you catch the bug immediately instead of trying to figure out which byte was misaligned on the wire, which is a real pain if you ask me. So another wonderful feature of the C++ enums is you can specify the underlying data type explicitly. In this particular case, here we have a definition of the standard USB descriptor for frame-based payload video format, and part of that is this DRM protection, whether it's none or no duplication. Yes, in C you could also use like #define and say none is 0, do no duplication is 1, but then in here you would have to specify something like byte or char size, or uint 18, the newer version, but it's not as clear because you could just as well use some other unrelated constants in this place. In C++, we explicitly say that no, this bcopyProtect can only be one of the values from this enum, and the size of the enum is specified in here, so we are adhering to the standard as it is defined. Concepts are one of the newer features of C++, and it's a very powerful one. It really greatly helps with diagnostics. You know, you've probably seen those horrible C++ examples of template metaprogramming when you have an error and you have pages and pages and pages of some obscure error message which is buried somewhere deep down. The concept is helping with that significantly. For example, in this particular case, we have a concept of any char, which is either a char or char16t. And then we just use it in here when we create a USB string type descriptor, which can accept either char or char16t based on this concept of any char. And if you try to provide it with an integer, for example, it would not be one of those types, and the compiler will promptly yell at you. And here is a example of how it used to be defined in C with this array, and you need to remember to put zeros in here, and you need to make sure that this 0C actually corresponds to the size of this whole array. And if you add like another dot in here, for example, you need to remember to update this number, otherwise it won't be valid. Or if you change this number without adding stuff in here, you also get into all sorts of troubles. In C++, it's all been taken care of automatically with a bit of boilerplate over here, but then the usage side is simplified and is error resilient. You just say make USB descriptor and it will create a variable with that name, and it will auto deduce the proper data type for it, and then you can just use it, send it back over the wire to the caller side. There are quite a few improvements of C++ over C that allowed us to write more expressive and cleaner code, especially when it comes to like name collisions that are fixed with namespaces, with default function parameters, when we can have multiple function overloads instead of adding subtle prefixes and suffixes to the function names. There are concepts that allow for error-resilient loops, for example, when you don't have to know the size of the array, you just loop through all the elements instead of trying to count them properly. Use of references instead of pointers. So all of this we'll discuss in these next slides. So namespaces. In C, everything is in one global namespace. And the side effect of that is that functions all have to be named differently. And you cannot, if you bring in multiple libraries, sometimes you have weird collisions which are not easy to find. In this contrived example, we have this super cool mass lib which defines a sign function, which just always returns 42. But then in our code we use ABS, which is a legit use of mass, and we also call sign, which unexpectedly in our particular case calls the one defined in mass.h instead of the one that we want to call, and it produces the wrong result. In C++, there is no ambiguity. You just say what namespace of the function that you are trying to call is, and it will be called exactly that way. Already touched a little bit on default function parameters, but that's one of the ways of reducing the cognitive load for a software engineer writing a program. Function overloads, again, it's just one example. The ABS function that has been overloaded to handle multiple different data types in C. There is one function for float, there is one function for long double that produces a float, there is also function for long longs, and all sorts of variations. Not only it's confusing, also you can't possibly expect software engineers to remember all those little like function naming conventions, which by the way are different in different libraries, so there is no like standard way of doing that. Again, in C++, it's just solved with proper function overload. Range for loops are a source of endless bugs in C. Off by one is one of the biggest issues, and it's completely, the whole class of bugs disappears with the use of range for loops. And as an added benefit on this slide, you can see that you can define the numbers as being auto, so you don't have to specify. It's a standard array of integers of size 1, 2, 3, 4, 5. So you don't need to do any of that. So when you add one more number into this array, you'll be sure that your printf will handle that number, or if you remove one number, which is not the case here. In C version, if you add or remove, you will need to remember to update this number over here for the size of the array, and you would need to remember to update this counter as well, which again is error prone. Pointers are a great feature when used correctly, and is a real bazooka pointing at your foot when it's used incorrectly. In C, it's a contrived example, but it is so easy to have a code like that when we have a pointer that we receive from some function somewhere which may not be initialized, and then we try to use it. And in an embedded system, you can't even check for null, because it is very often that the null value is one of the legit values. On top of that, null is not always a 0. On some systems, null is a -1. or some other value that is not valid for the system in that particular memory layout. So you can't rely on a numerical value of a pointer to make sure that it's a valid pointer or not for that particular system. C++ solves that by using reference. There is no way, well, no easy way, no obvious, unless you go out of your way to make this a bug. It's really easy to use it properly and hard to use it improperly, which is what I like. And here's a real-life example of range for loops, std arrays, and references instead of pointers, and all kind of stuff. You can read through the slide at your leisure if you stop the video here. So often in C code, I see bit manipulation done with bitmasks and bit shifting. Not only it's ugly, error-prone, it also does produce worse code than using bitfields in C++. I checked the compiler explorer, and 9 times out of 10 the code produced for more or less complicated bitmasks by the compiler is better in C++ than bit shifting in C. Attributes in C++ are another great example of express in the language instead of in the comments. Nobody reads comments. Not humans, not compilers, no tool chains, nobody reads comments. Not only they are like white space noise, they often and easily get outdated and incorrect for the code they are commenting. So on the left side you see the C example from actually sample code from Cypress for the UVC sample code, which uses this falls through comment. Would you read it? Maybe, maybe not. But when you just glance through the structure, you do expect breaks, right? So you look at this case and you think there is a break. Visually, it may not jump at you that there is a fall through. And then you would just look into this event and think it's done differently. And the compiler may or may not complain about that. And here it's clear. The compiler, if you forget the fall through, the compiler will yell at you, and rightfully so. Object-oriented programming, there are many competing views on its usefulness, but when used properly, it's a fantastic tool. Here's an example from real code. I have this I2C like base class, which does which provides interface for reading and writing. And then I derive a whole bunch of classes that have specific functionality. There is one for a generic I2C that I use just to check mostly for whether the the device is on I2C bus at this address or not. And then there is an expander, and there is a sound chip, and there is a fan, and there is a temperature sensor, and then there is an image sensor, and FPGA, and this and that, a whole bunch of devices which are all controlled through this standardized interface, where I just need to implement what's on top of that, the different one, but the base interface it's encapsulated in a single class. Resource management is one of the hardest things in low-level languages like C and C++, when programmers need to remember when you acquire some resource, the lifetime needs to be managed. Otherwise, especially in embedded system, you are asking for trouble. RAII, resource acquisition is initialization. I believe it's a horrible acronym for a great concept where when you instantiate an object of some resource type, you acquire that resource at the time of instantiation, and when you leave the scope of that object, the destructor takes care of properly releasing the resource. Here is an example of go-to, right? So the canonical C way, for example, in this case of processing a file, you open a file, and if it's not open, you return, and you try to lock it, and if it's not, you need to go to this block of done, which would unlock the file, because you don't want to leave the function without properly unlocking the file. And imagine some junior engineer coming later on and says, oh, by the way, if the file name is such and such, then we just return from here, which may bypass the go-to, go to done, which will bypass the unlock and def close, and it will cause a bug which is a horrible kind to find. In contrast, in C++, we just specify the guard object. We say file lock, we acquire it when we instantiate, and at the end, if it was opened, then we unlock it and close it. And then all you do is you have this file lock over here. You just acquire the file lock, you do something, you return cleanly without any problem, because the destructor will take care of releasing the resource. And then you do some work and you again return without a second thought. And no matter how many junior engineers come in here and sprinkle more return statements, the code will still continue being valid and correct. And here is an example of RAII in my production code, where this I2C access guard, which is, it doesn't matter how it's defined, what matters is in the read and in the write, I just say, here's my access guard, and I return, it simplifies the code significantly, whatever my internal function does, and the access guard will automatically release the mutex that is acquired when the read happens, and the same for the write. Another feature while on this slide is if constexpr. This allows for the conditional compilation or inclusion of the code into your code. That's funny. In this case, it is a clear replacement for the pound if defs. If, for example, in C version, it would have said if I2C use access guard, if pound defined, then include this statement, otherwise don't. In here, it looks much cleaner to my taste, and the compiler obviously is free to optimize this whole thing out if this I2C use access guard is defined to be false. In embedded, it is often to operate directly on memory mapped registers that represent some devices accessible from the CPU, and it is way more convenient to model those devices, abstract them out into structs or classes in case of C++, with some functionality associated with them. In C++, you can just state once, that's how I initialize, here is my address being defined by some value from some header file that was included. And then I just say my hardware GPIO pin is, hardware GPIO block is over here. And then I can just say that's how I access the RGB LED pin that I need to control, need to set up the LED controller with. In C, I see quite often that in embedded, especially code, the absolute abuse of globals to track the state of things around, which leads to a monolithic design with a single file that includes everything there is. So let's go through a few ways of how C++ handles that and helps with the maintainability and modularity. This is the initial state of our camera's firmware. Now, when I started working on it, when it was in C, it was literally a single file, more or less, with most of the code in it. And it was a real pain to even trace how the variables are being set and where they're being used and how they're being modified. It was a nightmare. In C++, the static in the function is guaranteed to be lazily initialized and only initialized once. It does come at a slight, like a few assembly instructions overhead, but it guarantees the proper initialization in a multi-threaded environment. So if you have a complicated C++ embedded project, you will be sure that this static initialization is done properly and you will never hit a race condition. User-provided literals are one of my favorite features of C++ compared to C. And here's an example of defining GUIDs I have this little struct GUID8 that defines basically a structure as it is, and then has a few methods to convert from string to string, arrays and stuff. And I have this consteval operator GUID. Consteval, first of all, means that it is guaranteed, absolutely guaranteed, to be run at compile time. If I try to run this GUID from code that is runtime code, the compiler will yell at me, and rightfully so. But what it allows me to do is to use this suffix now. I just have a string which represents my GUID, which is quite readable in this case, right? And I just say, no, I want it to be a GUID, which will call this operator, which will promptly convert it into GUID8. This auto will deduce, so my 4cc and v12 would be a proper in-memory representation of this GUID with all the bits properly placed in all these data fields. C++ 20 modules, even though they are not fully supported on all the embedded systems, and the support is still experimental even that many years later, it's still a great way of modularizing your code, of making sure there are no circular dependencies, and it helps with it solves quite a few problems that exist with header inclusions, which are listed. Some of them are listed on this slide. As always, everything comes at a price, and moving from one paradigm to another, from one language to another, is not immune, even from moving from C to C++. And for embedded environments specifically, here are some of the few things that I have, again, personally experienced and would like to caution you about. Heap memory is probably on top of the list, especially for systems with tiny and limited memory. You are not as free to use some of the standard library, like growing containers, like a vector, or some other features like new and delete, which is somewhat similar to not being able to use malloc and free in C, but still you need to be aware of those limitations, and if possible prefer to use static, not function static, but the global statics like translation unit statics and placement new instead of regular new. And if you absolutely need to have some sort of dynamic memory, you may look into using custom allocators. You can provide custom allocator, and then you're free to implement your own memory management in a way that exactly matches your requirements. So continuing on the STL, the standard template library, just generally prefer containers with static memory like std_array. It will save a lot of headache for you. Exceptions is another big topic in C++, while being a very powerful feature. And in fact, there was a great video recently by, I don't remember the name of the person, unfortunately, but he was digging into C++ exceptions and how they implemented, and he has found that re-implementing his I2C library using exceptions instead of passing error codes all around has in fact reduced the global size of the embedded code that was produced. You should probably check it out. It's in CppCon, I believe. RTTI, runtime type information, which is basically a necessity for dynamic cast, and it usually is also bundled with polymorphism. All of these concepts come at an extra memory footprint, and quite often can be replaced with a CRTP, which is curiously recurring, I don't even remember, TP type something or the other, which is essentially static polymorphism. And you will be surprised how often you can get away with just using CRTP instead of runtime information, which also, being static, comes at zero cost when the compiler is done with all the optimizations around it. Local statics in functions, as I mentioned before, they make sure that you avoid the static initialization order fiasco, but it does come at a few assembly instructions overhead. Just be mindful of that. So this is the end of slides, and one other thing I wanted to urge you to take a look at is this video on YouTube from Jason Turner that was in 2016 CppCon. But I gotta tell you, this video, just whatever, reject all. This video will shock you about the extent to which modern C++ toolchains can optimize your code. I mean, in this video, he implements a fully playable, I think, ping pong game, and it's just a handful of bytes when it has been all compiled and optimized. I really highly recommend you watching this video. I'll provide the link to this video in the description as well. And with that, thank you for watching, and I'll see you in the next video. And I'm guessing this computer will need to be updated and restarted and all that, so I will see you at the clean desktop next time.